this over here is this homework, see if there are any issues. Oh, my apologies. I realized this morning that I didn't do what I said I was going to do and cut down, but I think I said just don't do the ones with the multiple constraints. It was like 21, 22. If you did them, good job. It just was more algebra. That's basically what it is if you have more than one constraint, it means more algebra. But was there any of this, the early numbers that we can do? I refuse to do the and I also have a correction, not a correction, a completion of the work that I did yesterday. Remember, I had a problem and couldn't do my math. Well, I figured out my math. And it didn't take that long. It just took 5 minutes of looking at the problem. I'll show you my answer. But first of all, the homework for today, what do you think? Any issues that we need to deal with? Oh yeah, what do you think, Daniel?
Can you explain your reasoning?
Oh, the reasoning. Okay, so hopefully you can see with your eyes where the maximum and minimum values are. It's right here, because you're going to be, so I guess what I would say, just looking at this, I'd say it's obvious that down here you're at 30 feet, and that you're the trail, if you think of this as a trail, you're walking on this trail right there at that point, you're very close to 30 feet. And nowhere else is the trail as close to the 30-foot contour. And so I would say that's going to be the minimum for that reason. And then as we walk along the trail, we're at 40 feet, and then we go up to 50 feet, and then we go down a little bit, maybe closer to 50. And then we get up here, and we're very close to 60 feet. So at this point, you're almost at the 60-foot circle. So that would be my reasoning, is that it's unlikely that you're going to be closer to 60 feet anywhere but at that point. It could be that because of some weird topographic weirdness, there may be a steep cliff here, and all of this area here is all 50 feet except for the very line. So it could be that the maximum is elsewhere, but probably it's there. So I think that's the idea, is that it's not, you're not 100% sure that the maximum is right here. And just imagine for a minute that this is like a raised, what is it called? Like a raised platform, if you will, all 60 feet, and it drops off like a cliff. And down here, it's all just 50 feet, so that it's almost a discontinuity. In that case, you might be right there. You might be only 50 feet above sea level. And perhaps there's a little hill right here, right on this platform, or this, like over at Foundation Park, the little levels. So maybe that's what this looks like, I don't know. But if that's the case, then maybe the maximum is here or here, but it's probably there. So that's all. That's all that was supposed to be asking for. Oh, what is this? G of x, y is equal to 8? Oh, that's, oh yeah, never mind. That's the trail that you're on. So, is there anything else from the smaller numbers? If you really want to, we could talk about the bigger numbers, but I'll show you my mistake from last time. Yeah.
On that one, how do we get the values of that?
Oh, I would say that it's close to 60, because
that's the value.
The value? Yeah.
Would it just be 60?
So let's see, what is the maximum and minimum values? I would say that right there, you're probably close to 60. So if you want, you could like say, well, you're not at 60, so maybe it's 59 and a half. Yeah, pick a number. So yeah, you're not going to be precise. And here, you're probably close to 30, probably 31, maybe 30.5, maybe, I don't know. So probably, but same thing goes though. It's not necessarily true that that's the absolute minimum, because there could be some weird topographic thing going on here, but probably it's the minimum if this is a nice smooth function. Yeah, I guess I thought that there would be more questions about the actual calculations. Let me show you my my thing. So this was last time. You remember this horrible problem? Turned out it wasn't quite so horrible. I ended up resorting to using a computer, which was embarrassing. But then I sat down this morning. It took me less than 5 minutes. It was a few minutes, and I realized how I could do this much easier. So here's the trick. So that I used, I'll show you the actual math. It took almost no space as well. the trick I did was I looked at this and I thought, how can I make this simpler? And the way I can make it simpler is multiply this entire equation by x, multiply this entire equation by y, and multiply this entire equation by z. And at first you might say, well, that makes things more complicated, but what it does is it makes this xyz, this is xyz, and this is xyz. Then also I divided both sides by lambda, so I just had xyz over lambda is equal to these three things. And that meant, here we go, let me show you the work I did. No, that wasn't it. Here it is. So I basically just copied those down here, and then I multiplied, as I mentioned, and then I numbered these, 1, 2, and 3. And so what this means is that this thing in the parentheses is equal to this thing in the parentheses, which is equal to this thing in the parentheses. And so I just paired them up. This equals this equals this, and that was enough to get the solution. And the solution was super quick after that. So for here, I even numbered them here, that when you let 1 equal to 2, or no, 1 equal to 3, so 1 equals 3, this equals this, and you can see that you have the 2xz that you can cancel, and then after you cancel 2xz, you can cancel a y, and you're left with x equals 2z. And then I did the same thing for, I think I took 2 and 3, set them equal to one another, and I got something similar, y equals 2z. And I took both of those and stuck them back up here into this equation, so those two substitutions, and I got this. So here, I'll zoom out a bit so you can see it all. So I took this and this, stuck it up here for x and y, and I got 4z squared plus 4c squared plus 4c squared equals 12. Hopefully you can do that in your head, but if not, you get 12z squared equals 12, z squared equals 1, so z equals plus or minus 1. We're going to eliminate the negative, well, I guess we shouldn't, but so there's the z, and then of course, once you have z, x and y are 2 and 2. So the answer is 2, 2, 1, or negative 2, negative 2, 1. The final step would be to plug those numbers into the original, oh, I don't have it printed here, but the original volume of the box, and the positive numbers are the ones that make sense. So that's going to be your maximum volume. So yeah, so it turned out to be way easier. I just was floundering, and you know how it is. You sometimes can't see the forest for the trees, or I don't know if that's the right analogy, but so I just got lost in my lambdas. I thought lambda was important, and look, I don't even care what lambda is. Like, I didn't even compute lambda. All I got was x, y, and z. That's all I care about. So the lambda just disappeared. So yeah, the algebra sometimes is tricky. The algebra for today's quiz, though, is simple. All you have to do is remember the formulas, or the form, and the form is that you take the gradients, throw a lambda into one of them, and set them equal, and you'll be fine. So here, I'll put the quiz. Wait, I've got it here somewhere. Quiz, there it is. There's the quiz. So there's the quiz. I'll bring it around, but you can look at it. And I picked a nice, easy, and I double checked. It works out, at least when I checked it this morning, it worked out nicely. So hopefully it will continue to work out nicely. I will double check it when I get done passing these around. I don't know, is that you? Sure.
Yeah, it is.
All protein all the time. I think there's too many there. You can pass it back to Joshua when you get over here. Hopefully enough. There's 3, Joshua, you're going to have to, oh, you got 2 extra. There's 3. Oh, you need, I neglected my, sorry about that. It is. Recording. Sorry, there's an equals. There equals out of place. That should be a plus. Just a minute, I've got to erase. Just a minute. No, I double checked the math, but I didn't check there. That should be a +7 there. It wouldn't make a huge difference if you just eliminated the 7 altogether, because when you do the derivative, it's going to go away anyway. But put a +7 instead of an equals. I must have mistyped. This over. There we go. Looks like people are just leaving, so let's keep it while I'm finishing up. So if you are done, feel free to pass your paper over. This is for me. Right there. See if I got it right. So doing pretty good. Okay. Okay. All right, now set. Still working. All set. Oh, you're all set. Excellent. Good work. I see a lot of birds. You're not supposed to be raising. Keep going.
I had a bunch of wrong.
Oh, you had a bunch of wrong.
And then I realized what I did wrong. Okay. Now we're just seeing how to do this.
I remember one time, I think it was my freshman year, my mom was like, "What's your whale box?" Yeah. And I was like, I know it now.
I got a screenshot the other day for something old and they sent all the information and every time I just scroll back to the screenshot of my text message history. So yes. I should just write it down somewhere.
Oh, is that ready? Is that for me? All right, hopefully you're coming down the home stretch here, those who are still enjoying the process. But if you're stuck with the algebra, let's just get going, because it is algebra. It's annoying algebra. I try to make it as annoying, less annoying as possible. Well, yeah. You got it set up though. No, you got a good setup. Good job. Let's see. Did you set it up? Wait, you crossed it out. You crossed it out? No, it's almost right. Yeah. Here, I'll take what you have. And I'll give you at least most of credit. Most of credit. Now let's see. What do you have? Partial credit? You got something? Yeah, you have some numbers. Good. Numbers are good. Is that it? Okay, we're all done. Yeah, remember, these are worth almost nothing. I mean, collectively, they're worth something. Oh, do I have them all? Staples? Okay, it's official. Okay, so let's see how this is done. So what did I do? So hopefully I got it right. I got the answer that a lot of you had. And like I said, I'm going to try really hard not to have like that quiz last week that was nasty. I'm going to triple check everything. So this, I was happy it worked, other than I forgot to change that to a plus. But so you do the gradient, 3 and 4. How much easier could it be than that? And then over here, the gradient of g is just 2x and 2y. Now, at this point, I was tempted to do something different from what we've been doing, but I thought, no, no, no. I need to do it exactly the way you're going to do it, but I will show you a trick in just a minute that will make life easier in cases like this. So I'll show you in just a second what I mean by that, but what I did was I took I took f, or the gradient of f, is equal to lambda times the gradient of g, and I just took each of the components. So 3 is equal to 2x lambda. So there it is there. Okay, now you can see it all. So 2x times lambda, and 4 is equal to 2y times lambda. Now here's the trick that you could use. Because we don't care about lambda, all we care is that lambda is just a scaling factor. You could have put the lambda on the other side, and it would have made the algebra a little bit easier. I mean, if you got stuck with the algebra over there, it was probably because of this. Now, if you put the lambda on the other side, so it was 3 lambdas 2x, it actually works out super nice. So, but I decided I'll do it the way you're probably doing it. And so I got this. I solved each of these for x and y. And I saw a lot of you did this. There were a few minor hiccups with your solving. But here's my x and here's my y. I plugged those into this original constraint up here. So the x squared plus 2 plus y squared is 25. And I got this. So that is just this constraint with the x and the y that I got. Carefully doing the algebra. So yeah, you make one mistake, it's a snowball. It gets worse, doesn't it? So anyway, there's that. Did a little bit more algebra, and then I guess I skipped a step here, but you can combine these into a single fraction, 25 over 4 lambda squared. Multiply both sides by 4 lambda squared, divide both sides by 25. You get 1 is equal to 4 lambda squared, or lambda is plus or minus 1/2. We don't care about lambda, though. It's just the way it is. But if I'd put the lambda on the other side, I would have gotten lambda is plus or minus 2. It would have been a little nicer. Whatever. So then I just plug these into my equations. So remember, x is 3 over 2 lambda. So x is 3 when lambda is 1/2. Y is 4 when lambda is 1/2. And when lambda is negative 1/2, I got negative 3 and negative 4. And that's it. Those are the 2 points. And then I plugged them into my original function, and I got the max in the middle. So that's what I call a nice answer. I try. So I don't want you to feel like on an exam, if it doesn't come out nicely like this, doesn't mean you're wrong. It might mean that I'm wrong, and I made a mistake. So don't feel like it's going to always, but I will try. I try, but I can't guarantee results. By the way, I was so curious about this one, I actually graphed this. So that's right here. And here you can see that plane. I know it's kind of steep, all that blue plane. But on the plane, I have the trail that you're walking. And you can kind of see, whoops, well, it's almost straight up and down. It's a very steep hill. But you can see down here, there's the minimum. Up there is the maximum. So it looks elliptical, but if you were to tilt this so that you're looking straight down on it, it would look like a circle. Okay, I probably can't. That's about as good as I can get it. Tilt it up a little bit more. It'll actually be circular. So that's this circular trail, well, seen from above, but it's actually incredibly steep. Okay, let's move on though. Today we get to move on to a topic that hopefully will be much less painful. We're going to find out. I know that looks painful, but it's not as bad as it looks. So today we're not going to deal with that in particular. We're going to be doing what's called iterated integrals. And in order to understand iterated integrals, you need to understand those. Do you know what those mean? I hope you do. This is the indefinite integral. So that's the thing that you're looking for an antiderivative of f of x, and it generally is defined using something like the fundamental theorem of calculus, or it's just defined out of whole cloth as being the function whose derivative is f of x. And that's where the c comes in. You get the c because there are a bunch of functions whose derivative is f of x. On the other hand, this is a definite integral. So that one is a definite integral. Definite integral. And in general, we thought of that as being an area underneath the curve f of x. So that we would draw a picture like this, and you would have an A and a B, and this is the area under this curve. As you might imagine, when we deal with 3 dimensions, our integrals are going to mean something slightly different. Instead of being areas, they're going to be volumes. And so that's where this picture comes in. Now, lest you get scared that I'm going to make you do, whoops, not that, there we go. Lest you get scared that I'm going to make you do Riemann sums, I'm not. Although I should, but I won't. So this, by the way, is a picture of a Riemann sum in 3 dimensions. You see, back in the old days, the first encounter that we had with this definite integral was in terms of area. We didn't, at least at the time, in Calc 1, have the equipment that would require us to use the fundamental theorem of calculus. And so we divided this into rectangles, just reminding you of the fun you had, and then computed the area of each of the rectangles, did a limit as the size of the rectangles shrunk to 0, and that would be the area. Same thing is true in 3 dimensions. You could do something similar, but we aren't going to, don't worry. I'm going to skip that section because I don't find it super useful. You've done Riemann sums, been there, done that, don't want to do it again. But we do need to talk about what this means. And having this in mind, by the way, this will be essential to understanding what this means. So there will be times that I refer back to pictures like this, even if I'm not going to make you compute this. I think you can figure out what this means is that we find the volume of each of these boxes. There are 16 of them. And that volume is approximately the same as the volume underneath that curve. So let's go to this, though. Today, we're just going to be dealing with this sort of thing. What does this mean? So what we mean by that symbolism is we mean that we're going to do an iterated integral. So here, I've got the word up there, iterated. Whoops. Iterated integrals. So it's an integral, it's iterated, we're doing 2 integrals, and this will hopefully harken back to derivatives. You know how when we did derivatives, you did the derivative with respect to x, and you ignored the y. And when you did the derivative with respect to y, you ignored the x. So over here, I'm going to do the integral. So if you imagine just this part here, I'm going to do the integral of this stuff with respect to y. I'm going to ignore the x for a bit when I do that. And then I'll do the same thing. I will treat the y as if it doesn't exist. Well, it won't exist, to be honest, once we get to the outer integral. So here's the way that we're going to do this. We're going to start by just focusing on that inner integral from 1 to 3 of xy dy. I think you can all do this. In fact, I'm so confident. I'll just pick someone out of the blue. This reminds me that I need to finish doing attendance. Where is my attendance? There it is. I never clicked submit, so I will submit it now. Yes, okay, I got it right. Okay, there. That's part of the reason why, you know, I much prefer randomizing on my phone, but I've got this now. I can use this, and it also reminds me to do attendance. So Cooper Stiegel, what is the antiderivative of xy with respect to y? Okay, you treat the x as if it's nothing. Let's ignore the x. Do you know what the antiderivative of y is with respect to y? I know, I'm hitting you up. Well, you just got up out of bed, didn't you? So you can do it, though. Here, let's pretend it's just, let's go back. Let's make it easier. What's the antiderivative of x with respect to x? Oh, no. Okay, you're still waking up. Let's skip. We'll come back to you. All right, Cooper? Don't worry. maybe next time I could bring you like a double shot latte or something to help you out. But for now, let's move on. Briar, your neighbor here, you're going to help. Do you know what the antiderivative of y is with respect to y? 1/2 y squared. Yeah, now it's like, oh yeah, that's right. It's okay. It's okay. I've been there. I was there yesterday morning. Remember? That was terrible. But anyway, so ignore the x for a minute. So we have y squared over 2. And then y is going to go from 1 to 3. So notice that the x is not the variable I'm interested in. So it is treated as if it were constant. If that were the number 5, you would get 5y squared over 2. So I know it's hard. It's so hard for you. I saw that on your last test when you have multiple variables to sort out which one is important. How can we discriminate against the x? It's okay. X will get its turn in the sun. For now, y is the important variable. X is meaningless. Well, it's not meaningless, but we're going to ignore it. Okay, so a couple of features that I want you to point out, or I want to point out to you, is when I'm integrating with respect to y, I put a little y here. This is not something that you've been trained to do because we've been in single variable land. But now that we have multiple variables, it's going to be important to know what your limits are. Like, is it x or is it y? And because I'm integrating with respect to y, these are values for y. So that's the first thing that I want to note. Also, the x is just a constant. So now let's plug these in. So here I know, so Cooper, you can redeem yourself now. Cooper Stiegel, what do you get when you plug 3 into there?
9/2.
Okay, so but we're gonna even though the x we're treating it as if it doesn't matter. It does matter to some extent. We're just gonna keep it around. We'll say, okay, you can stay here, but we're not gonna really treat you that well. So very nice. And then we need the lower limit. Let's see. So Caden, what do you get when you plug that lower limit into this? Yeah, so x over 2, 1/2 x is fine. So there is my inner integral. Let me just combine these. We get 8x over 2, which is the same as 4x. So that is the inner integral. Whenever you have an iterated integral, you can do this. You can take the inner piece, separate it, just put it aside, do it, and then let's go back and stick it in there. So let me go ahead and stick that in there so you can see what it looks like. This will be the integral from 1 to 2 of 4x dx. So notice that this thing ends up right there. So let me just pause, make sure everyone's happy, or at least not too sad. Okay, so let's go ahead and do this inner integral, or outer integral now. Joshua, you know the outer integral. What's the antiderivative of 4x? Very nice. So that's going to be 2x squared. If you're not quite as quick as Joshua with your integrals, remember that this is going to be 4x squared divided by 2, because you add 1 to this power, and then you divide by the power, and then 4 divided by 2 is 2. And then notice that once again, I am putting, even though it's kind of unnecessary here, I want to get in the habit, and I'd like you to try to get in the habit also, of writing down your limits in terms of which variable is important. So are we integrating with respect to x, or is it with respect to y? You can't just assume that it's x because of this. And there's going to be times when you have an answer that looks like this, but you're going to plug y into it. No, I don't think there's ever going to be a time like that, to be honest. But I just realized, yeah, that's never going to happen. But yeah, I can't think of a function that would do that. So, but there's going to be some where it's going to be ambivalent, like, or you're not going to be sure. So let's go ahead and let's crank this in here. This is easy enough. Oh yeah, let's go ahead and pick 2 people. Daniel, what do you get when you plug 2 into all that? Yeah, you get 8. And then Tyler, what about when you plug 1 into all that? 2. Yeah, a minus 2 is 6, and that's the total. And eventually we will say that that is the volume. We'll describe this as a volume. But for now, I just want to practice. That's all today is practicing these iterated integrals. So we have to practice a few more, and there's some nuances that I want to make sure I point out. So let's try this one. So let's try this. I know you're looking at it thinking, well, drat. It's okay. It's okay. It's going to be fine. So see how much you can do with this, and I'll even rewrite. Let's see. Let's just take that inner part and stick it over here. Oh no. There we go. Okay, so let's just deal with the inner integral. That part right there, and see how we do. See. All right, I know you're scared of this, but I think that it's not as bad as it looks. I mean, it looks pretty bad. But remember, here's the saving grace of this. You're integrating with respect to y, and so this e to the x squared doesn't matter. It's x. And this x over here doesn't matter. It's just x. So all you have is just y to the first power. That's what you're integrating. And Kelsey, you know what the antiderivative of y to the first power is, don't you?
It is y squared over 2.
Very nice. And all the rest of the stuff just goes along for the ride. So I'll write it like this, maybe x e to the x squared, and then I'll get that y squared over 2 and stick it in there. So if you have something like this, you can rejoice that you're just dealing with the y. And we'll have to come back and we'll have to deal with the x eventually, but we'll do it later. So, okay, now we can plug and chug. Let's see, I'll just do this. This ends up equaling 2x e to the x squared. Double check my math though. I know I just skipped a step there of writing everything out, but I think you can all do this. Does that look all right? All right, no one's yelling at me, so I'm going to just put this over here. You got to let me know though, because you remember yesterday, things went off the rails. And so I think I'm better today, but who knows? Okay, so this thing will equal the integral from 0 to 2 of 2x e to the x squared dx. So notice that I just take this thing over here and I stick it in right here. There, just to indicate, all I did was I took my this thing, pulled it over, did the work, pushed it back. We're all good. So let's see if we can do that inner or the outer integral. The inner integral is the first one, the outer one is the second one. So I think you can handle this. I'll give you a minute though to ruminate. And we'll see how we are. Well, Ryan, what do you think? What are you going to do? How are we going to do this? Or you could just tell me what the answer is.
I'm not sure.
Oh, okay. Okay. So do you have any ideas about what you might do to this to make it easier?
Are you going to have to use the product rule?
No, let's not use the product rule. By the way, the product rule is when you do integrals, the product rule is the what is it called? Integration by parts. So it's not the product rule, it's actually the chain rule. Do you remember what the rule is when you integrate? I know that he's got it back there. But okay, what is it? Yeah, go ahead. Yeah, it's U substitution. You remember this now? Yeah, I tried to make it obvious that you got x squared 2x. Anytime you see something like that, it's like, oh, wait a minute, a function and its derivative. Let's use U substitution. So just as Caden was symbolizing with his hands, making the U, U is x squared. And so du is 2x dx. And so when I do this, I'm going to get, let's see, I'm going to rearrange just once here. 0 to 2 of e to the x squared 2x dx. So just so you know, I'm always going to do this where I rearrange so it looks exactly like du, just the way that I do it. You might be able to do it in your head, but I want to make sure because substitution can be tricky. So this is going to be the integral of e to the u du. Now, one other thing that I'm going to do, I used to do it differently, and but it seemed like people would do the wrong thing. So what I will do consistently is when there are limits with a substitution problem, I will drop the limits, do the integral, and then I'll put the limits back in when I get done because those limits are values of x, and here I have u. And so if I put the limits there, they would be wrong. Granted, I could change the limits to values for u, but I don't, that's what I used to do, but that seemed to cause more problems than it was worth. It seems like most students learn to do substitution like this, where you just drop the limits and then, so just bear in mind, these are values of x. So if you write them over there, yeah, just it's better not to. Okay, now we can do this antiderivative. Emily, what's the antiderivative of e to the u?
E to the u.
Yeah, it's our favorite function, isn't it? E to the u, which in terms of x is e to the x squared, using the substitution that you can see up at the top, down here. Now let's plug in our limits. X, oh, come on. So x is equal to 0, and x is equal to 2. And that's going to give me e to the 4 minus e to the 0, which is e to the 4th minus 1 as my final answer. So not too bad. I mean, we had to do a substitution, but that's okay. So just bear in mind that sometimes you'll have to do substitutions in the middle of some sort of a double integral. It's a little bit painful. Let's see. That one, let's not do that. Okay, so some in your book, so the problems that you're going to have to do are going to look something like this. So, or some of them, I should say. So whenever you see something like this, what it's indicating to you is it's saying we're going to do a double integral over a region. So x values and y values, if you put them together, you get sort of like a rectangular region. If you think about it like back here with this problem, this would represent, you could represent this with the region from 0 to 2 in the x direction and 0 to 2 in the y direction. So that would be the region that I'm integrating over because the x values and the y values go like that. So sometimes we're going to see something like this. Is this the one I had up? Yeah, it doesn't matter. That's the one we're going to do. So let's see if we can work this one out. And the reason that it's done this way is because you might want to integrate this one way or the other. Or here, a better example. Well, yeah. Oh well, too late. I guess we'll do this one. Okay, so let's see. This one's hard. Is this one hard? No, it's not that bad. Yeah, let's do one that I know for sure I can do. If you don't mind, it's very similar. I know you've got that written down. Just put some space and we'll do this one first. Because I know for sure I can do this one. But I'm scared now of that other one, even though it looks to me like it might be an arctangent. I love arctangents. But this one I know because this one's a good example of why you might want to set this up one way rather than the other. So there's two ways we could set this up. Once you have your sort of the range of values, your region, you can set this up in the following two ways. Either, so bear with me for a sec here, either you're going to write it like this, where x goes from 0 to 1, y goes from 0 to 2, of xy e to the x squared y dy dx. Or, here's the other option. You could integrate, whoops, with respect to y, whoops, I just want to erase there. So y goes from 0 to 2, and then x is on the inside, xy e to the x squared y dx dy. So you have two options. So whenever you see something like this, you can choose. Oftentimes, it won't matter. It won't matter at all which one you choose to do first and which one you choose to do second. In this case, it does matter which one is first and which one is second. So oftentimes it doesn't matter. You can pick whichever way you're most comfortable with, and probably the way you're most comfortable with is going to be this way on the left. Well, let's examine this one on the left just briefly. And you can probably guess by what I just said that this is not the way that I'm going to prefer to do this. So if we were to do this in this order, then we're going to do the inner integral first. So the y goes from 0 to 2 of xy e to the x squared y dy dx. Now, in order to do this, I'm going to have to use some sort of technique. And the technique that you're forced to use here is integration by parts. So integration by parts. Which I'm guessing makes some of you sad. And so if you're sad about that, let's check out the other way. You certainly could do this, but it's going to be kind of painful, kind of ugly. So let's go over to the other side and see what that one looks like. So let's just write down the inner integral. So I left the dx there, just a minute. Let me get rid of the dx. That shouldn't, well, come on. There. Get rid of the dx. So integration by parts makes us sad. I mean, over here, this is also going to require some work, but hopefully, well, I don't know if this is my preferred way of doing it, because this way is going to require us to use integration by substitution. U substitution, I feel like that is a more commonly, you're more used to U substitution than you are used to parts. Okay, this is going to be okay, so that one, maybe I'd do this. There. Okay, so over there you're sad. This way you're like, well, whatever, I can do it. Okay, so let me just put this over in Notability so I don't have to deal with all the scrolling. Just a sec, done. Copy and delete. There we go. Isn't that beautiful? Stick it here. All right, yeah, looks good. Okay, so let's do the substitution instead of the parts. If you really want to use parts, you can, but I'm not going to here. Okay, you can do it on your own time. It'll work, but it's just going to be a lot more work. So over here, sometimes, well, here we'll do that in a minute. Okay, so over here, what we've got is I'm doing this right here. So I think you could all figure out that the u is going to be x squared y. And so the du, and here, bear in mind that the important letter is x. So it's not obvious, but we're going to do this with respect to x. So du is 2xy dx. So I'm doing the derivative with respect to x here. I mean, mainly it's because of the dx there. Okay, before I can do this substitution, because of the way I do it, I have to, x equals 1, rewrite this like this. Now let's take a look at what just happened. I moved the x and the y over so that they'd be next to the dx, and I magically made a 2. But you know how this works, is I can carefully, write 1/2 here so that it balances. But now I've got this direct substitution for du. That's the hardest part. At least I feel like it's the most important bit. Now that I can do this, let's see, this is going to be 1/2 e to the u du. So take a look at it. 5 minutes, we've got this. We're going to finish this. So you got that part? I know some of you are like, I could never have done that. Yes, you could have. It's a basic substitution. I know there's a y there, but it's there. It's going to be okay. Okay. And now we all know that the antiderivative of 1/2 e to the u is 1/2 e to the u. And that is equal to 1/2 e to the x squared y, using this substitution here. Okay, so I'll pause, make sure no one's lost their minds. All right, let's cram this back into the original expression. So let's see, that's right here. Right here. This thing became this. So I have the 1/2 is still there, e to the x squared y. And here x is going to go from 0 to 1. So this is going to be 1/2 e to the y minus 1/2 e to the 0, which is 1/2 e to the y minus 1/2. Halfway there. I know. But fortunately for us, the rest of this is super easy. So you see that the benefit of me doing it this way is we ended up with a nice, easy outer integral. I mean, that's another problem with this way, is that if you did it with integration by parts, you get done with integration by parts and you're still not out of the woods. There's still tons of work to do. Here, we just do the substitution. Almost done. Let's do this outer integral. Here, y goes from 0 to 2. And this is 1/2 e to the y minus 1/2 is the integrand dy. See if you can do that. I'll bet you can. I'll pick a person to help me with it. All right, Nolan, you know what the antiderivative of this thing is, don't you? Yes, you do. Don't tell me no. What's the antiderivative of e to the y? Very nice. So I'll just put a 1/2 in front of it. What's the antiderivative of a constant? Well, the constant is 1/2. 1/2 times y. Very good. See, you know your antiderivatives. Y equals 0 to y equals 2. Don't be scared by fractions and e's. Okay, so now that we've got that, we just plug in 1/2 e to the second minus 1/2 times 2 minus 1/2 times e to the 0 minus 1/2 times 0. And I think this all ends up being 1/2 e to the second minus 3/2 when all is said and done, because this is 2/2 and this is 1/2 gives you 3/2. Whew. Okay, let me go back to PowerPoint land, make sure that there's nothing else that I need to deal with. Let's see, volumes. So when it says a volume is the same as a iterated integral. It's the same thing. So if you see on your homework a volume, you're going to use this. And the only other thing you need to know is that you need to take whatever function, if it's not already written in terms of x and y, you need to rearrange so that the function is x and y. I guess that you guys are being mutinous and saying that we need to end now. Okay. If you do have questions, though, it's all on you now because we didn't finish. Well, I think you can handle it, though. So I'll stop the recording. Come talk to me if you need to. Otherwise, have a great day.